Today we're going to start by talking more about arc length. We're going to define the arc length function in the following manner. S of t will be this integral from a to t of the length of r prime of u du. Let me show you what I mean by this. We're given a vector function r of t, say t running from a to b, and this vector function defines some curve in space, like this, where we're starting here at r of a. Again, that's the vector from the origin to that point, but we're thinking about that as starting at that point in space and ending here at r of b. And we're moving along the curve in that direction. Now, what is s of t? Well, at any point with parameter t, say we're here at r prime of t, s of t is the length of the curve from the initial point here until you get to that point with parameter t. It's the length of this piece of the curve. Let me draw that in here in green. That would be s of t. And for different values of t, you'll get different s of t. As t increases from a to b, we'll see that s of a is 0, just the integral from a to 0, from a to a of the length of r prime of u du, and s of b is the total length of the curve. Of course, the length of r prime of u du is just given by this familiar expression now, the square root of dx du squared plus dy du squared plus dz du squared. We're using u here as our parameter instead of t because our variable t now is in that upper limit. This arc length function will help us understand motion along the curve. What is the derivative with respect to t of s of t? Well, by the fundamental theorem of calculus, it says the derivative of a function defined like this, where t is here in the upper limit, is just the integrand at t, so that will be exactly the length of r prime of t, which is exactly what we've been calling v of t. This is the speed function. Notice this is the length of the velocity vector. R prime of t is the velocity function. And so this tells us something very natural. If we want to know how far we've gone up until, think of t as a time variable, up until time t, we're starting at time a and we're going up to time t, all we do is integrate our speed function from t, starting with t equals a and going out to whatever t is. So it's a very natural concept that our total distance traveled, which would be the length of the curve up until that point, is given by an integral of our speed function. That's all this is saying. We want to talk about several things that will help us understand motion along a curve in space. Remember, we're starting with r of t denoting the position on some space curve. So I'll just draw it again like this. We're starting there, we're moving just as before in that direction, for example. We know that r prime of t is this velocity vector, and at any point on the curve, r prime of t will be a vector in the direction of motion tangent to the curve. Here, r prime of t will look like that. But the length of this velocity vector, r prime of t, just depends on how fast the object is moving along the curve. And that depends very much on the parameterization. Just imagine this vector function r of t describing not just the curve, but motion along the curve. The tangential direction is defined by the geometry of the curve, but the length of this velocity vector, that's the speed function, depends very much on the parameterization. It's not just dependent on the geometry of the curve. Now, if we want something that depends only on the geometry, we define what we call the unit tangent vector. This is capital T of t, called the unit tangent vector, and that's just this velocity vector divided by the length of the velocity vector, which is the speed function. This will now be a vector of length 1, that's why it's called the unit tangent vector, and it will be in the tangent direction. So what is that? What's special about that? Well, at every point along the curve, this unit tangent vector will be tangent to the curve because it's just a scalar multiple of the velocity vector, which is already tangent to the curve, but they'll all have exactly the same length. Wherever we are, it'll be a unit vector, which just tells you in which direction the curve is pointing. All vectors have exactly the same length here. And that's now something that's purely a geometric quantity associated with the curve. It doesn't matter how we reparameterize the curve, the unit tangent vectors will be the same. Now we want to talk about this notion of curvature, which essentially should measure how curvy a curve is. And what does that mean? We want the curvature to be really a high number when a curve winds around a lot. At least at most points here, you're going to have a very high value for the curvature. But if you have a curve which doesn't bend all that much, like that, we want to say there's a small curvature. So the curvature will be, we want this in the end to be a function of our parameter t that will tell us at any point how curvy is the curve near that point. You see, even here, the curvature would be very low in this region, but in many places, the curvature would be very high when the curve bends quite a bit. So in most places on this very curvy curve, the curvature should be high. Just similarly, in most places, the curvature here would be pretty low, higher here. How are we going to get a reasonable way to measure how curvy a curve is? What will make sense? Well, we'll want to know kind of how fast the direction of the tangent vectors change. And if we want to know how fast the directions of the tangent vectors change, we want to look at these unit tangent vectors, which are really a good measure of, at every point, of what direction we're going in, and ask how fast do these unit tangent vectors change. They change only in direction because their magnitude stays the same. So if those unit tangent vectors are changing very quickly, that means the curve is bending quite a bit. Now we could look at the rate of change of this unit tangent vector. Remember, this is a vector function, so it should be boldface, or if you're writing it, you should have an arrow, a vector hat on it. We could look at dt and ask how fast is this unit tangent vector changing with respect to the parameter t. That will be a vector quantity, so we might just take the length of that and ask if that's a good measure of the curviness of a curve. But this will depend on the parameterization. If the parameterization has us going very slowly in an area, then these unit tangent vectors will similarly be changing very slowly, even if the curve bends a bit. So even on a very curvy curve like this one, if the parameterization has us moving very slowly around here, that would give you a very small number for the curvature if we defined it like this. The way we actually define it is that the curvature, and we use a Greek letter kappa, which looks like a K, but that's a kappa actually, a Greek letter kappa to denote the length of this vector dt ds, the rate of change of the unit tangent vector with respect to this arc length. Now what does that mean? If we have a curve, there are many different ways to parameterize it that would correspond to moving along the curve at different speeds. If we use s, our arc length function, as a parameterization, just think of s as a variable. When s equals 1, that means we've moved 1 unit along the curve. When s equals 2, we've moved 2 units along the curve. So using s as our parameter, that kind of corresponds to moving along the curve at a constant rate of speed, 1 unit of length per unit of s, whatever that is. So it's kind of a constant speed parameterization when we use the arc length as our parameterization. But this is then pretty abstract. How are we going to compute dt ds, and which will be a vector function, and then we want the length of that to give us a numerical value that tells us how curvy it is. Well, just by the chain rule, dt ds is dt dt. Let me actually write that a little bit differently. I apologize. dt dt is dt ds times ds dt. This is just an expression of the chain rule. If I just divide by ds dt, I get that kappa here is equal to, let me rewrite it. Kappa, which is the length of dt ds, is the length of dt ds. Again, we divide by ds dt, and we get dt. Oh, actually, I apologize. I should have seen this here. I have that written down right here. Kappa, which is dt ds, the length of dt ds is the length of dt dt divided by ds dt, which is, and another way to say that is just that it's the length of t prime of t, that's dt dt, over the length of r prime of t, because that's just ds dt. Remember, ds dt is exactly here v of t, not the vector function, v of t, the speed function. We talked about that, the speed function, v of t, which is exactly the length of r prime of t. So this is a way we can compute kappa. Now, I'm not going to go through the derivation, but in the book they actually show this. You can compute the curvature kappa of t in this way. If what you're given is your vector function r of t, you compute r prime of t, which is very simple, just use differentiation. You compute r prime of t, compute r double prime of t, which means compute, differentiate again in each component. Take the cross product, and this is only, here, this is only in three-dimensional space. I mentioned that because everything else we did will work in any number of dimensions, but if you happen to have a space curve in three-dimensional space, kappa of t will be r prime of t cross r double prime of t. Take the length of that and divide that by the length of r prime of t cubed. That seems a very strange formula. As I said, the derivation is in the book, but it gives you a handy way to compute kappa of t that's applicable in some circumstances.